Just to recall, the goal was, I just recalling you that the goal was the following. So we have a linear time for a moment, time invariant filter. Okay. So everything is stationary now. So for the sake of reasoning, is not adaptive. So it's simply stationary. Everything is stationary. So the goal is the following. So we have the input xn, and we measure the input. We have the output theta, and we measure the output. Okay. And we have a system, linear time invariant system, and this linear system is depending on a set of coefficients that I call A0, or A optimal, or A true, or A whatever. Okay. So my goal is to replicate the same system and change A, the coefficient A of the filter, such that this coefficient replicates the same coefficient A0. And when they replicate exactly this coefficient, the error, which is theta hat minus theta z, theta hat minus theta, okay, is the residual, the error, what remains, is only depending on the noise, because the noise is not in any way predictable, because the noise is something that is statistically independent on xn. We assume that xn is a stationary process. We assume that w is stationary. We assume that a0 is constant. Okay, so we are looking at the adaptive system from a point of view where everything is frozen, at least frozen in terms of non-stationary. Okay, so it's a stationary, this phenomenon. And so my goal is to identify, so if you estimate A, and this coefficient A asymptotically, which means after many iterations, they coincide with A0 up to the noise effect. That's the goal. Okay. So in making that, we wrote our objective function. And we found that the objective function, I'm making a summary, and we found that this objective function, which is minimizing the mean square error, this objective function depends on A. A is the unknown. Okay? So these are the unknown. And we immediately spot that this is a quadratic form. So my goal is simply to minimize this quadratic form. So I can do it iteratively. The reason to make it iteratively is because I don't invert the matrix R. And the matrix R, which contains the autocorrelation of X is the input, so it might be very big. So the size of the matrix R is the size of the filtering A. So A is a filter, which is this filter here. Okay? So the matrix R depends on this filter. If this filter is very big, the matrix R is very big, and if I need to invert the matrix R, which is very big, the cost of the inversion is n cubic. Okay? And the reason why I gave you the two examples, which is one is for active noise cancelling, which is for headset, okay, and the second example was for telecom students, or at least all the others can appreciate what is the real problem that the telecom people they need to deal with, okay, wireless telecom people, is that every sometime, where sometime might be millisecond, so every millisecond I need to calculate the coefficient A0. Now, if I need to calculate the coefficient A0 every 1 millisecond, every half a millisecond, that means that the cost of inverting the matrix R, which is the order of n cubic, might be too complicated or almost impossible. So for this reason, I need to find a way where perhaps I approach a solution not exactly straight away, but I can do it iteratively. And I gave you the example that when you open a web page and you don't immediately see the picture, but you see a fuzzy picture. That is the case where the information is popping to the screen incremental. Okay, so we are making similar that incremental, which means at the beginning of the iteration, you know, this is not exactly perfect, but you know, it's refining step by step. Okay, so that's where we are. And so what we did, I'm repeating because you know it makes sense, because I'm making a new parallel now, a new derivation. So what we found is that we can optimize this quadratic form by iterative methods. And what we found, you know, we found that the step size that we need to design to converge should be smaller than a certain value. Okay, and this certain value depends on lambda max. And lambda max is the maximum eigenvalue of the matrix R. So everything depends on the matrix R, and the step size depends on you know, the eigenvalue of that matrix. Now, taking the problem and decomposing the problem into the principal axis, okay, so remember we have the quadratic form and we decompose into the principal axis. So when I take the, you know, the quadratic form and optimize the quadratic form with respect to the principal axis, what I can find is that I can find a set of parallel problems. So rather than having one iteration, I have many iterations that are running in parallel. So it's like to have a set of iterations that are linked together, I put it together by the choice of the same mu step. Now, if I make it this way, it's similar to, here, is similar to having to optimize on every of these directions this quadratic problem, which is now is a parabola. So in other words, you know, if you have these contours of space and you set your axis along this direction, and you call this one as a Z1, this is Z2, and if you optimize your gradient search, and you go down, 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 down until you reach the minimum, okay? This is equivalent to have a problem on this direction and a problem on the other direction. Now, since in this direction, you know, the quadratic form is steeper, but you know, the steepness depends on the eigenvalue. So since the quadratic form in this direction, which is the zeta 2, is steeper, that means that lambda 2 is bigger. Now the convergence is quicker. And on the other hand, along the Z1, which is the curvature depends on lambda 1, the convergence is smoother, is slower. Okay? Now, so that means that if I look at the convergence in this direction, the other direction, I can decouple the behavior of the convergence. So that means that, you know, in every direction, I can see the optimization problem as if, you know, I'm jumping this way. Or perhaps, you know, I make a very, very big step. And then, you know, I can make a mistake, or I make such a big step that I go to the other side. Now, the convergence condition, beyond the mathematics that we did the last time, okay, Friday, the convergence condition is simply saying, be careful. When you start from one point, never make a big step to go higher than before. Okay? So remember, if you need to ski and you want to you have what is the bombardino, you know, you don't know what is bombardino, the foreigner doesn't know. Okay? So it's you know, when you after skiing, you go to the bar, which is at the bottom here, and then you drink. Okay? And so you enjoy after, okay? And then you go up and down, and you know, this is the hobby that you do for all day. So, you know, now, if you are here, you want to go to the bottom of the valley. I mean, if you really want to go to the bottom of the valley, you don't want to make this being, you know, bouncing. Okay? Because, I mean, you always go close and then you go on the other side. Go close and go on the other side, okay? So you keep going up and down. So to avoid that, you know, the optimum lambda that prevents any fluctuations is not 2 divided by lambda max, but 1 divided by lambda max. So the condition, so this condition, okay, this one is mu smaller than 2 lambda max. But if I don't want to go to the other side, but I want to go possibly to the minimum, possibly in one step. I need to make, I don't want to do this way, but I want to do the other way, which is I start from here and I want to go there. Or I start from here, but I don't want to rebound on the other side. So if you want to prevent a convergence with fluctuations, that the choice is half of the previous one. And half is mu is smaller than 1 over lambda max. 1 over lambda max is a convergence without fluctuations. Okay? Convergence without fluctuation means, I don't go down, get close to the bombardino, which is the drinking, okay? I go to the other side. Okay? I want to go straight there, which is minimizing the energy, the energy spent to reach the bombardino. Okay? Okay, so then how much time I take to converge. Now the time for convergence depends on the slowest one. So if we start running together, since I'm the slowest one, and we want to declare that we all reach the destination, you need to wait me. Okay, that I might be the slowest of you. Okay, and then since I'm the slowest one, now I dominate the time for convergence. So the time for convergence is the ratio between the lambda max and the lambda min, where lambda max is because of the convergence condition, and lambda min is because of wait for the slowest. Okay? So we are a group of people, we need to go to the bar, down to the valley, and in order to go down to the valley and declare that we are all drinking together, you need to wait at the slowest one. And so the convergence time is approximately depending on that. Now, don't forget that when I declare this time for convergence, the convergence is always exponential. And so this is the subtangent. So this time for convergence is related to the subtangent. So now let's continue on that. So since the convergence time depends on the ratio between lambda max and lambda min, remember lambda max of the matrix R and lambda min of the matrix R. Now if I start with a problem, how do I get this lambda max and lambda min? So as a paradox, I have the sequence, I have a random process, I need to take a covariance matrix, I need to calculate the lambda max, lambda min, and then I finally can get the convergence time. Okay? But lambda max, lambda min is what the mathematician call condition number, okay, or is what we call the eigenvalue spread, which is the ratio between lambda max over and lambda min. But right now it doesn't say anything to us, except to give a name, okay. So there is a theorem that we will prove a little bit later now, is that the eigenvalue for a stationary process is proportional to the power spectral density. So there is a theorem that is saying something similar. So lambda I of a specific covariance matrix, and this covariance matrix, remember we are zero mean, so covariance and autocorrelation matrix is the same, coincide. Okay. So now the lambda I, so the eigenvalues of a specific covariance matrix, okay, for stationary xn, okay, this one is in some way proportional to the power spectral density calculated to a particular omega for the same process. For a particular omega, okay, now this omega is, and we call omega k, okay? So the relationship between lambda I and omega k is a little bit not trivial. Okay. But what is important is that if, if we say that the eigenvalue is approximately correspondent to the power spectral density, remember, this is the power spectral density of X. Okay. So if that one is corresponding to the power spectral density, then lambda max, the maximum eigenvalue, is the maximum power spectral density. And lambda mean, which is the minimum of the power spectral density. So I come out with a very useful relation, which is telling me that the ratio between lambda max and lambda min, which is defining the convergence time, is approximately similar to the maximum of the power spectral density and the minimum of the power spectral density. That's a ratio. Okay? So that means that if I look at now, if I have a magic possibility, and in case I don't have this magic, I can estimate the power spectral density, which is part of the spectral analysis that we will do later. So the reason why I'm moving the adaptive filtering now instead of the regular order is because I want to do the workshop, this exercising. When is it? 2 weeks from now. Okay, I will send you an email about the logistics. Okay, so the reason is I anticipate, the adaptive filtering now because I want to do that one. So now, if I have a power spectral density, so look at this one. Imagine that this is the power spectral density, the one on the left. So if the one on the left is the power spectral density, now what matters to me is the ratio between the max of S omega and the min of S omega. Okay? And now, if I look at in logarithmic scale, this distance is the ratio between lambda max and lambda min. Okay? If it is a logarithmic scale. Okay? So in log scale, let me write it. Okay? In log scale, that means that the log of max of X divided by min of X, okay, can be written as log of max of XX minus log min of XX. So it's a distance, okay? So the ratio becomes a distance. And that's why, I consider that as a distance. So that one is, the condition number of the matrix 4, which is proportional to the time of conversion. Now, the difference between the solid line and the dashed line is that this ratio for the dashed line, we change the color. So this ratio for the dashed line is smaller. So that means that, the dashed line problem should converge quicker than the solid line because the lambda ratio is bigger. Okay? Now, if I look at the quadratic form corresponding to this behavior, the quadratic form are approximately that one. So, the solid line quadratic form, okay, which is the one where, the eigenvalue are very spread one with respect to another, okay, is this one. And so the quadratic form is very narrow. So when I start from here, I start bouncing, and slowly I go to the minimum, So this is what happens when it's very narrow and elongated. Okay, so this is what's happened for for the solid line. The dashed line, which means that the eigenvalues are when the power spectral density is pretty flat. Then my quadratic form is very much circular, and then my convergence is, let me say, kind of easy. Now, if the power spectral density is constant, okay, So what's happening? If the power spectral density is constant, that means that we are dealing with a white process. We have a constant here, and the quadratic form are composed by circles. The contour line, okay, of the quadratic. And then, you know, for the circle contouring, my convergence is straightforward. I go immediately to the bottom, okay? That's the optimal. So, now, question to you. Question to you. Now I'm triggering your intuition, okay? So, assume that you start with the power spectral density that is like this. Okay. Unfortunately, this minimum is a disaster because this minimum and this maximum, you know, creates the eigenvalue dispersion that is too big. Okay? How to combat that? You have a random process, right? That has a power spectral density that is too spread. And you know, and you would like to have a power spectral density that is flat. Or if not flat, you know, with the less deep hole, how would you do? Remember, you can, you know, as I was mentioning with some of you Friday, you know, I'm providing you a box with tools. And so you need to pick up the tool that you need to solve the problem, okay? So you are not different from plumber. The plumber is just using a different tool. So you are not better than him or her, okay? You are using simply a different set of tools. So now I'm asking you, what tools, what kind of tool you might use to put yourself in the position of dashed line, which is more convenient, that is faster convergence, than the case of a dipole like that.
Pole cancellation. As you showed us in MATLAB, we can
okay.
draw the poles.
So this is a 0.
Yeah, that one is 0.
So I can put the pole. Okay, that pole, you know, is in some way pulling up this notch. Okay, that's a good choice. But you know, more general, what you can do, you can filter, as you were saying. So you can filter X to flat, to make it as flat as possible, the power spectral density. You don't need to make a perfect filter. Okay, the zero cancellation, you know, you need a perfect pole. And it might be time consuming together. But it's enough, you get a kind of flat power spectral density. Now this is called a whitening filter. So you can make a whitening filter. The whitening filter is a filter that is creating the inverse of the filter itself. Okay? Because if I cascade the filter with the whitening, you know, I get a white process at the end. Okay? Remember, white is not only the noise, white is the process. Huh? It's a property of the process. Okay, so you know, if I repeat that, I mean, I can apply a filter. Now read this, and this is describing the same. Now, how can I make it better? Remember, we are not adaptive yet. We're simply reasoning. I'm simply, you know, practicing you on the story of reason on the gradient. Now, if I need to accelerate the convergence, looking at the formula, and since I learn how to study the formula beyond the formula, beyond what the formula is telling me, if I look at the formula, I can see that, you know, this is, I have a set of coefficient. So this A hat is a set of coefficient. So I have A1k plus 1, A2k plus 1, ANK plus 1. Okay. Hat. Okay, this is what is written there. So I have a set of coefficient. So I have a set of coefficient that are updated, okay, by a new term. Now, but I mean, what is the bad story for convergence is that if I need to update, okay, and I want to go to the bottom here, the bad story is that I need to wait for the slowest one. So what is the it's not the error. What is the limitation of the method? The limitation is that since I choose the same step size for every skier, okay, then you know the step size going in this direction is the same step size going in that direction. But now, what about if the step size going in this direction is, you know, let me say, slowest? Then in this direction I make one step and I'm here, and then I make a big step and I go the other direction. So I can reach the minimum in 2 steps. Now, what does it mean? It means that, you know, I can change the step size. I can make the step size shaped according to the problem on the principal direction of the problem itself. So I can make a step size different in this direction and the other. Now, it's not trivial that way. So the only way is that, looking at the formula, mu is a scalar. Mu as a scalar means is one number which has to be, it should be make happy everybody, okay? So it's like, you know, I'm the slowest one, you have the faster one, and you know, but I constrain you to make the same small step. Now the reason why we reach the destination at the same time is that I make a small step and I constrain you to make the same small step. What about, you know, if you make a step, but you know, you push me to make a bigger step because I'm the slowest one, then you know you're better to make a bigger step. Now in this way we reach the destination in the slowest time. So how do I modify? Now what about if rather than take a mu as a scalar, I use mu as a matrix. So if mu is a matrix, means that I can calibrate a different step size according to whatever direction I'm considering. Now, this is specifically making mu as a step as a matrix, okay? And you know, I can easily check that if mu is equal to the inverse of the matrix R, I can reach a destination in one step. Now, we will continue on that because this is the essence, this is the key idea of a recursive least square. Now, okay, so let me say, this is just to put you into the topic. Now, everything we said up to now, okay, is on iterative convergence. Iterative means I have R, I have P, so R is the autocorrelation matrix, I have the cross correlation vector, and then I start iterating, okay? So up to here, you know, I know up to here, R and P are known. Now what we do now, starting from here, R and P are not known. And so we slide into the iterative adaptive filter, okay? So now, you know, what is the adaptive filter then? You know, that means that what we need to do is, we need to, here, we write the same filter, so let's consider, now we are in the passive. So let's consider the coefficient AN, the filter. And the filter is, you know, is A minus K and A minus K1 plus 1, blah, blah. And then I have AK2 minus 1 and AK2. So, you know, I have a filter coefficient that is the length of the filter is K1 plus K2 plus 1, okay? So this part of the filter is causal, and this part of the filter is anticausal. Okay? So the filter that contains K1 coefficient on the anticausal part and K2 coefficient into the causal part. That is the most general one. And you know, in general, you can consider K1 very big, K2 very big. Now, so what I need to do, I need to estimate theta hat. So theta hat is estimated by taking the coefficient AK, and now I have a new term, which is the iteration. So this n is referring to the sample that I'm considering. So I have, a set of coefficient that is filtering, is taking x. This x is the convolution part. So it's taking the filter A at the n iteration, is taking the filter x, and then, is filtering, is convolving. By the convolution, I get a theta hat. Okay, similar as before. I'm computing similar as before, the error. Okay. Now, the major difference with respect to before is that the coefficient of the filter is n dependent, which means time varying. Okay, so this one is time varying, is a time varying filter or time varying estimator. It was easy before because the coefficients were fixed. Now the filter is time varying. Okay, so I rewrite my objective function, and now when I rewrite my objective function, I'm using a set of values. Let's say I use n values. So I'm computing, the sample mean of this mean square error. Okay, so this one is the sample mean square error, sample by n samples. Now, when I expand this, okay, blah 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 blah, what I get the same quadratic form, except that the quadratic form depends on the estimate, the sample estimate of the autocorrelation matrix and the sample estimate of the cross correlation matrix. So these are, the sample auto cross correlation. Okay. So now, the problem is the same, except now, is by using a set of values. If you like, these, in a machine learning, it's called the learning stage, okay? So these are coming from the learning stage. So these are coming from a set of coefficients that I know. Then, I can compute the P and R in this way. Now, apparently, the problem is the same, except that before we used the expectation, and now we use the sample estimate. Okay. Now, let's see. So I can compute, similarly as before, I can compute the gradient, okay, and then I can compute the adaptive filter. Once again, I'm computing, I am updating the sample autocorrelation and the sample cross correlation. Now this procedure is, is optimum when I consider a number of samples that is going to infinite and the random process as a stationary. Okay, so now if you can try. If the number of samples are going to infinite, then the sample estimate of the cross correlation, autocorrelation are going to the true value. And if it is stationary, then my unknown filter is stationary, and this converges to the same solution we saw before. Now let's move to the case where everything is not stationary. So we have seen that we have all the analytics that we need. So now, rather than computing as is indicated here, rather than computing the gradient, okay, using all the samples or the data, I can compute the gradient of the error using just one sample. In other words, if I write, let me copy it so I show you. Put it here. I put here just for convenience. Okay. Now I put here. Okay, these are in yellow is what I copy and paste from the previous page. Now you know if I look at the function, you know, when I need to compute the gradient as the one I computed on the top, okay, I am collecting the set of coefficients. So in other words, it means that if I need to filter something, I need to wait for a certain time before taking an action. So you know, sometimes this is not efficient. I mean, it's like to have a active noise cancelling system where the people is moving and then we say to the people, okay, wait a minute, don't move. You calculate the filter, bam, and you cancel the noise. You cannot do it because the head of the person keeps moving. And so that means that you cannot wait until you compute completely the error for computing the gradient. Because of what we do is we compute the gradient, we update according to the gradient. So rather than doing it this way, the extreme case is that my cost function is not the sum of n entry, it's a sum of 1. So rather than having a set of summing n errors, n, lowercase n, okay? So I have error 1, error 2, error 3, error 4, blah, 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 error 100. Okay, you wait 100. You calculate, you know, the sample covariance or sample correlation, autocorrelation in this case, as is zero mean. So you wait so long, then you make the filter. Okay? You cannot do that. You cannot do it because, you know, I mean, the time is running and you need to make the filter in real time. Real time is, you know, very fast, okay? So rather than make it that way, the one on the top, okay? So you make the extreme case where, you know, you approximate this one by theta n minus a n x n to the square. Which means rather than summing many, I compute the mean with just one value. So, you know, it's like if I ask you to calculate the mean of something, what you do, you calculate a set of samples and then you average, right? So, you know, if you need to calculate the mean, what do? You calculate, you say, okay, I have you know, I have an A1, X1, X2, X3, X20. So what do? You make this one. If you need to calculate the mean, then you divide by 20, right? This is what you do. Okay? Now what I'm asking you is, the extreme case is that x1 is the mean, x2 is the mean. Because x1 is the mean when I have one coefficient and the coefficient is 1. x2 is the mean when I have one coefficient and the coefficient is x2, and so forth. So similar there. So what's happening is that, you know, I'm computing the cost function where rather than averaging n samples, I'm taking 1. Okay? So this is the extreme case. Now, you know, how I'm sure that this one works. Now, first of all, you know, I mean, let me manipulate that. So I consider this extreme case, and you know, I know that this cost function for one sample is approximate, is not true. Okay? So, you know, in order this one, and by the way, this is the cost function for n samples. And in the previous pages, we considered the case where n is going to infinity. So what we did up to now, we did the following. So we made iterative. Iterative means that we have R and D. Okay? That means that we are computing the expectation. Okay? That means that we have, you know, equivalently, we have an infinite number of samples. Then what we did, we computed the adaptive. But you know, the adaptive, we split in two ways. One is that we have n samples. And when we have n samples, we can calculate r hat on n samples. And we calculate the p hat with n samples. And you know, that was very helpful because, I mean, if n is going to infinite, this coincide with r and this coincide with p. And we go back to the previous problem. Now we are taking the extreme case that the number of samples n is equal to 1. And in this case, you know, I don't have the possibility to compute the ensemble, which is the mean here. We don't have the possibility to compute, you know, the sample correlation with n big. We take just one sample, one value only. And that is what I calculated. So, rather than, you know, making the sum over n, I'm making sum to 1. You know, sum to 1 means 1. Okay? So, I am aware that this is an approximation. It's a very strong approximation. So what I do the following, you know, I take this as an approximation, I calculate the gradient with that, and I implement the gradient with one value. Now, what is the major difference? The major difference is the following. Remember, you know, my goal is to go to the minimum, okay? Because minimum, you know, I solve the problem, so I get the estimator, okay? Now, if I make the instantaneous error, because that one is the instantaneous error, because it's the error computed by one sample only, that one, okay? So if I make just instantaneous value, so my error surface is not that smooth. So my error surface, imagine that I'm sitting here. So I don't see a very smooth surface. It's equivalent to see a very bumpy one. And so when I take a decision to go in a certain direction, and perhaps, you know, I don't know, for some reason, the gradient, according to me, seems to be 0. Because, you know, I'm a small mountain, you know, when you ski, you know. When you ski, I mean, when you go to ski, if you never ski, okay, I was skiing, but you know, now my leg doesn't support me. So, you know, but if you go skiing, what's happened is that you try to smoothly go down. You try to avoid stones. You don't see stones. Stones are behind. They are a small valley, okay? So, you know, the beauty is that you ski. That's why the people like to ski in the fresh snow, because everything is very smooth, you know. But when you go to ski after a lot of people are skiing, you know, everything is rough, okay? And if you go at the end of the season, it's very bad, okay? They say bad snow. So, you know, now you want to go to have a bombardino. You know, remember, that's the way. The goal is always that, okay? And so you have your friends skiing quickly, you are the slowest one, but they wait to you. And, you know, and if you're slow, after a while they don't wait anymore, they go skiing with someone else. So, you know, because that's the bad story for the too slow people. Now, then, you know, you try to go skiing, but remember, what is the instantaneous error? The instantaneous error is the following. I'm skiing, I am on a stone, okay, which means I am here, you know, for some reason there, okay, this is the stone, and then, you know, I'm calculating the instantaneous gradient. And, you know, what about if the instantaneous gradient points me in that direction? Okay, what I do, you know, I move my ski and then I go there, right? Okay, now, I'm not going to the bar, I'm going to another place, right? Now, you know, how to compensate for that? Now, the way to compensate is, I don't trust this measurement. I don't trust the gradient that I calculate from an instantaneous value. What I do with that, I move a little bit. I move less than, you know, knowing the perfect gradient. So rather than, you know, taking this value and the new factor says move up to here, I say I don't trust you. I move a little bit. I make a small step. Then I recalculate the gradient. Then the gradient says, no, you have to go there. Then you start going. Then you start moving. So, you know, if you keep moving, at the end you reach the min. Okay? So the statement is move, continue to move, but don't make a big step. Now everything can be supported by better theory rather than the picture of a scheme. But let's see that. So now this is the instantaneous error. So if I take this instantaneous error and I put into my gradient formula, remember the gradient formula is an plus 1 is equal to an minus mu time gradient with respect to a is divided by 2 for the reason. And this is the gradient search. So if I plug this one there, and what I get is the new relationship. Okay, this new relationship, is called the least mean square update. And the method is called the least mean square adaptive filtering. Okay, it's because the rationale is this least mean square update. Now this is also called the stochastic gradient. Now stochastic gradient means the story that you make a small steps, which means you calculate the gradient by averaging a lot of small steps. So you make a set of small steps, and now, by the way, the small steps are the instantaneous gradient calculated with one sample. So the instantaneous gradient calculated with one sample, you put together with the instantaneous gradient calculated with the second sample, third sample, fourth samples, and so on. In this way, you get the gradient. So you calculate the gradient by summing instantaneous gradient and moving in the middle, in the intermediate. So let's read it. Let's read the formula. So I have the filter at iteration n plus 1 is equal to an plus mu. Mu is a step size. Epsilon is the error, but the instantaneous error. So is this one. Okay. So that is the instantaneous error. Where is it? Here. Okay. This is the instantaneous error, and this is the input. The input that I give. Okay? Now, the formula is so stupid. It's so simple. In implementing, it takes one line. One line. Okay? Now, it's in the past. Now I never seen more enthusiastic people. But in the past, in the 80s, in the 90s, the people were enthusiastic implementing the LMS method. Okay, it's very simple, and they started to implement everywhere. When I say everywhere, I really say everywhere. Okay, any problem they try to implement the LMS. Any problem where it's a non-stationary, or it's stationary, but it's slowly changing or similar. They implemented the LMS. Okay, it cost nothing. Is this you have already to compute. The error is just is a sum. Okay, so the cost is the cost of a sum. So you have the error. This is the vector of the input. The vector of the input is n times 1. Mu is a scalar. So you have a scalar times a scalar, one multiplication. Okay. And then this one multiplication is multiplied by n number. So you have n plus 1 multiplications. And the update costs n plus 1 multiplication per iteration. So every new sample, n plus 1 multiplication. And every sample, n plus 1. I skip the n multiplication that comes from the filter because you need to compute the filtering anyway. Okay, so I don't take into account these multiplications because they are not relevant. Because you need to filter anyway. So the multiplication I'm considering is only to update the filter. If you make this way, you get the convergence as far as you choose mu properly. Now, this mu has to be totally reconsidered because it's different from the previous one. When we made the iterative, everything was static. And, you know, we can calculate the mu value in that case. Now we replace the gradient with the stochastic gradient, so the instantaneous gradient, the instantaneous error. And we need to reevaluate what is the mu, the optimum mu step. Now, let's see. So we need to make the convergence, so-called convergence analysis. So we need to calculate, convergence analysis is how to compute mu. Okay, this is reading this line. How can I compute mu? Now, consider the problem. I sketch here. Consider the problem of identification, which is the easiest one. It's not the only one, but that's the easiest one. By the way, perhaps you know, during the break time, I searched for the book of Witherell. There is a famous book. Okay, it's a book where I studied. Okay? So you know, it's a book where I became an enthusiastic about the adaptive filtering. Okay, now you know I'm doing a different job, but you know I also had my time where I was one of the enthusiastic about applying the adaptive filtering. Okay? Now, so I searched the book. There are a set of examples, and then I can show you a set of examples from the original book by Witherell, where you can see different applications. But I will make it during the breaks. So anyway. What is the convergence analysis? So the problem is as we described before. Okay, so we have we have a filter. We have xn. Xn is entering here, and the output is affected by the noise. And I have a filter with a coefficient A0. Let's keep this station. A0. Okay. And this is what I call data n. So, what I calculate, this is my system, okay? So this is what I want to infer. Okay? So I replicate in parallel a system where I call this data hat. This is the error. And now, let's look together before we continue. Let's look together the formula. The formula says, now you take this error, okay? And here there are an, is a coefficient of iteration n. So if you want to get an plus 1, you take a set of measurements. You take epsilon, okay? You take the value of an, and then I read an plus 1 is equal to an plus mu times epsilon, an, x. So I combine all that into the computation of the gradient, and then I update with an plus 1. Now this branch does not exist because I can keep in memory here. Okay. So the adaptation, is trivial, if you think. Okay. Because implementing this form, this is very simple. Now this line, is, let me put it in dashes because the set of coefficient I can memorize into the update formula. Remember, I have n samples that are entering there, okay, and I have one sample here, and I have a set of n sample coefficient entering into the upper part. For instance, if you perhaps go to spend the Erasmus in Germany, okay, at the Technical University of Munich, my colleague there, represent the scheme in this way. So when there is a vector that is running into the problem, it indicates with the two lines just to indicate that it's not a one-dimensional signal, but it's multidimensional. Okay, so it's only a matter of notation. So anyway, okay. So we need to establish, the convergence, and the problem for convergence is this one. Okay. So now, I calculate the output, and then I have the error there. Now, if I consider, so look at this. This is my unknown. And now, to study the problem of convergence, I need to put myself in the same condition that I was working with in stationary process. So everything is stationary. Let's consider stationary for the time being. Okay? So if it is stationary, everything is there. I need to calculate what is the step size, mu, to make this an converge to that one, even if I'm using a stochastic gradient. Okay? Stochastic gradient is the one where I compute the error with instantaneous error. Now, the problem is more complicated, and then I try to give you the view. So first of all, look at the two analytics. I try to keep it simple. Okay. Look at the two analytics. So this is the same update. So this is the error. The formula is the same. So this error, so on. Okay. So it's only different way to write. Okay. So this is the LMS formula. Okay. That is the LMS. It's different. What you see here, what I see here is different from what you see there. I don't know why. Okay. Strange. Anyway, so so this is the LMS update. Now, if I need to calculate the convergence, the way to calculate the convergence is to define the error in the filter. So, what is the convergence now? So, what I want to have, asymptotically, I expect that this AN is going to A0. So, that means that AN minus A0 is the error in the filter coefficient. So, I call this one delta AN. So this delta AN is the error on the filter coefficient. Okay. Is error on filter. It's not this error, it's the error on the filter. Okay? So I expect a filter like this, and I get a filter like that. Okay? That's the error I consider. So now, how do I define the error? So these, in order to calculate the convergence, I need to have this delta AN to go to 0 when n is going to infinity. Fine? But this, since A0 is deterministic parameter, AN is a stochastic. And the reason why it's a stochastic, it comes from there. So this error is theta minus that one, but theta contains the noise. So, unfortunately the noise, since the noise is not predicted by anyone, is floating into the error. And the error is severely affected by the noise, which is floating there. So for this reason, when I write the error and I calculate this delta A, which is AN minus A0, and I plug into there, okay, plug means I just rearrange. What I get is that this delta AN is equal to a certain matrix delta A n at iteration before plus mu x noise. So, in other words, okay, if this is converging and if this is going to 0, this is going to 0, but you know, this is not going to 0. This keeps fluctuating. So I have a random stochastic term that is affecting by convergence, which was not existing before. So this means that at the convergence there is a residual anyway. So let's consider the skiing. When I go ski, even if I reach the minimum, I keep moving. I keep moving. Okay? Now the easy way to avoid to keep moving, if I take this mu and put this mu to 0, then I stop moving because I don't make any step. Okay? Now, that means that I can define now two criteria for convergence. Now the criteria number one is to make the expectation for that going to 0. Now, making the expectation for that going to 0 is that I calculate the expectation of delta, and calculate the expectation for delta means that the estimate is unbiased. So, you know, that means that if I calculate, let me go to the other side. So if I calculate the expectation of delta A n, but according to the definition of the expectation, this is the expectation of A n minus A0, because this is deterministic. So if I guarantee that asymptotically this one is going to 0 for n going to infinite, then what's happened is that this is equal to that. So this guarantees that the expectation of A n is equal to A0. And that means that the problem for the system is asymptotically unbiased. So this is called convergence to the mean, or in mean convergence, okay? Which is equivalent to unbiased. To have the estimate that it is unbiased. Now, you know, we have another kind of convergence. The second convergence is the convergence in a mean square. What is the convergence in the mean square? The convergence in the mean square says that I want to guarantee that the expectation of delta A n squared, which is the variance now, this is the variance, okay? This is going asymptotically for n going to infinite to a certain value, c infinite. This is smaller than infinite, which means there's a constant value. Okay? This is called the convergence in the mean square. Now, let's see with a picture for that. Now, if this is guaranteed, then you know that if this and that is guaranteed, we have the adaptive estimator that is asymptotically unbiased and has a limited bias. If you remember, it's similar to blue, right? Blue was best linear bias estimator, right? So best, we try to minimize the variance, okay? Linear is linear, unbiased, asymptotically unbiased estimator. So now, let's see visually, what does it mean? Visually, it means the following. If we consider the first case, so if we consider that, you know, we choose a mu coefficient such that we guarantee the convergence in mean, okay, the upper part, the upper convergence only. So what we get is the following, remember, this is delta, I represented here delta AK, is the deviation with respect to the true coefficient, okay? So asymptotically, it has to go to 0. So which means, I expect that asymptotically this is going to 0, okay? But what's happened is that, is that when I start from a point arbitrary, so I have a filter, I don't know how to initialize, I initialize randomly, I initialize whatever. I initialize from the previous iteration, I initialize, okay? So I initialize, and then I keep the iteration running. This is bumping up and down, but at a certain point, it's there. Now, the convergence in the mean says that no matter how this guy is fluctuating, it's fluctuating around mean, and the mean is 0. So the convergence in mean means that the error on the coefficient keeps fluctuating, and perhaps for n going to infinite, it's fluctuating, it's diverging the fluctuation. So it's similar to the random walk. The random walk is, you always, in the mean, you always stay there, but the variance is growing, okay? So if you take a random walk, after a number of steps, very big, then you can be everywhere. So this is similar. You can keep fluctuating, then rather than staying here, which is what you expect, they start to diverge. Okay? So this is not what you want. Because if you have your filter and you expect that this is behaving as that, and you expect that this one are doing here, not there. There is noise here. They're creating the same signal, okay? So you don't want that to mean the signal that you recreate here is the same in mean, which means it's going this way, but it's fluctuating, okay? On the mean is the same, but not it's not the same, okay? So the convergence in mean, we do nothing with that. In other words, if you implement the convergence in mean, and you implement the condition for the convergence in mean, you come to me and you say, you told me junk, what you say is not true. It's not converging. It keeps fluctuating. It's unstable. Okay, this is what you say. It's not stable. The filter is unstable. I don't know, I cannot control. No. So we can see that the convergence in the mean makes a mu factor smaller than 2 times to lambda max, which is what we found before. And and is bigger than a certain mu mean square. The convergence in the mean square, the second one, you can read there, okay, is smaller than the convergence in mean, so it's more restrictive, okay. But it guarantees that, this is bouncing, okay? Now, since a mu, look at here. Now, this is a big mu, but since this mu is smaller than that, okay? So, bigger, so smaller mu means a bigger time for conversion. So, it takes more time to converge. It's slower to converge, okay? So, it fluctuates, it fluctuates for a longer time. But after a time long enough, this is fluctuating within a certain bound. And now this is the convergence in mean square. In other words, now look at this picture, look at that, look at this. Okay, so this one is saying I convergence in the mean here, but not in the mean square. I'm not saying anything about the variance. The second one is I converge in the mean square. And now we see that this is more restrictive. So what we see is that, mu factor, if this one is the range of mu should be bigger than 0. This is the mu axis. This is due to lambda max. will find a certain coefficient, it is, how do I call it? Mu v square, correct? Mu v square, which is smaller than that, such that if you make a choice of mu lower than this, so if you stay in this range, okay, the algorithm convergence is slower, but in this interval, I guarantee the convergence in the mean square, which means, you know, I don't have the amplitude that are diverging. This is the operative condition where you want to have the algorithm. Now, how to compute analytical? Is it clear intuitively? Okay? So, intuitively, you know, if you like, I mean, cutting here, that means that the dispersion is growing. Okay? Similar as the random walk. You know what is a random walk process? You have 0. You make with a probability 50%. I'm here. Okay? I started from the 0. Okay? This is where I start. Then I make with 50% probability, I make a step here. And with 50% probability, I make a step back. Okay? You know, and then I start. Okay, then when I'm here, I make with 50% step back and step forward. Here. I make with 50% step back and step forward. Then, you know, I keep going. Okay? And you can prove, check in any book. Okay? Check a random walk. You have a Google. You know, you need to use your Google, right? Not only to see the movie or YouTube, which is nice, but, you know, not only for that. Oh, but your YouTube is good. Okay. You are the only YouTube that you have to see. So anyway, but you know, so I mean, if you check, you can see, and you know, there are a lot of that. Okay, check YouTube or random walk, or I mean, read something like that. So you will see that I mean, the random walk process is a process that in the mean, the person is staying there in 0, but the variance is divergent. Okay, so that's similar. Now, in the second case, okay, I'm limited. So after a certain point, I mean, my dispersion is constrained. Okay, so the variance of delta A k infinite is equal to C k k infinite, what I call C k k infinite, which is the variance of the dispersion when, you know, my time frame is going to infinite. Now, up to now is only graphical. Huh? So, now the convergence in mean is stupid. Okay? You know, it's stupid because it's simple to see why it's stupid. Because if I look at, by the way, everything depends on the definition of delta A. I'm going to keep it there. Do I have it here? No. Everything depends on that. Good. Let me cancel that, because I prefer to stay on this side of the board. Delta A n plus 1, which is equal, just copying that, is a certain matrix, identity minus mu, and this is a vector transpose delta A n, okay, Q plus mu x n double n. So the convergence in mean is stupid because I simply calculate the expectation of delta A n or delta A n plus 1. So I apply the expectation here, I apply the expectation here. So when I apply the expectation to the noise, you know, the noise 0 and goes away. Okay? So, you know, applying the expectation here, expectation there means that this is the matrix R. So when I apply the expectation on both sides, let me write it this way. I mean, applying the expectation on both sides, here on the right and the left. So what I get is I have a delta A n plus 1 is equal to identity minus mu R expectation delta A n. The expectation of that is 0 because, you know, the noise is 0 mean. X is 0 mean. And the product is 0 because they are statistically independent. Gaussian, they are correlated. So this is the formula. But you know, if I go back, this is the same formula for the convergence of the iterative method. So same as iterative method. And then it comes out that mu should be smaller or equal than 2 over lambda max. This is what comes out, okay? So the most difficult part is the convergence in the mean square. Now I'm not proving that because, you know, otherwise it's going to take 3 hours. I'm not proving that, okay? But I give you the result. The result is very complex, so that's the reason why I move straight into the result. But you know, even if I move straight into the result, I need to give the opportunity for those of you that likes to go deeper into the analytics to see what is the rationale, how to make it. Okay, so let me comment on that. This is, you know, this is what I was mentioning, the convergence to the mean. Now, how to make it that? Convergence to the mean square. Now, in order to calculate, I mean, what I'm saying is, let me say, proof, let me write this way, proof is not required. Okay? So, but you know, let me tell you how the proof is obtained. So in order to evaluate the covariance, the convergence in a mean square, I need to start from the covariance. So you start first by defining the covariance, which is, you know, obtained by the definition, using the definition. Then in the covariance, what I'm interested in is the terms along the diagonal, because the terms along the diagonal are the variance. So I want to calculate the variance on the first, variance second, third, fourth, fifth, and coefficient of the filter. And this is a vector. I'm sketching, okay? So this is the vector of variances of filter or estimated coefficient. Now my goal is to find an iterative formula which is telling me how the variance is changing. So how is the formula for changing variance? Now when I manipulate, which means go to appendix, okay, when I manipulate, I get that the variances at iteration n minus 1, n plus 1 is equal to C to B matrix times the variance at iteration n plus a certain, you know, a certain term that depends on noise. I made, to make it simple, I made the assumption that the covariance of W is sigma square W identity. So, you know, the noise is uncovered. That's another simplification, okay? So, the matrix P, and that lambda is the vector of the eigenvalues. So, it depends on the eigenvalues, and it depends on, you know, on a certain matrix B. Now, intuitively, you know, if this is converging to infinite, now once I got this, let me tell you how to manipulate this formula. Once I got this, it doesn't matter how complicated is that. But what I want, this is the variance, okay? It's a vector of variances. So if that one is converging, what I need to get that the Cn plus 1 is converging to Cn for n going to infinity. So for the infinite, if that one is converging, the term on the left and the term on the right should be the same at convergence. Okay? And so, you know, I can find the value. And so I can rewrite this one for infinite, and this is a C infinite, which is the set of vectors containing the variances to infinite is equal to B C infinite plus mu squared sigma squared W vector lambda. And so what is a C infinite? You know, C infinite is simply, so I take B, move on that side, okay, and then calculate the inverse. So this is equal to identity minus B to the minus 1, okay, multiplied by mu sigma squared W lambda. So I found the set of variances. Now I need to find the B or the mu coefficient such that this is fulfilled. That's the conclusion. Now, you know, the complication comes because B is a function of mu itself, and it's a function of K. K is called kurtosis, and the kurtosis of the signal depends on how the signal is dispersed. Bigger kurtosis means that the signal is very much dispersed. So is a ratio between the fourth moments of the signal x, of the process x, divided by to the square of the second moment. Okay? So beyond the definition, you know, it's becoming kind of complicated. When I move on that, this is the complication. This is what I was mentioning to you. Is already, extracting in sequence. Blah blah blah. Here it is. Here it is, the complicated part. Blah 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 blah. You know, and then it comes out the easy formula. The easy formula is the same. Is this one the same? Is this? Is that mu should be smaller or equal than 2 times the sum of the eigenvalues, which is the trace of the matrix R. So the condition for convergence to the mean square is that the mu should be smaller than 2 times the trace of the matrix R. But the trace of the matrix is the sum of the powers. And the sum of the power means that I need to calculate the power of the input, the instantaneous power, sum in the power, and I calculate the mu according to that. It's very, very easy. I need to include one additional line to my code. Okay? So this is, the trace of R is 2 divided by sum of, along the diagonal, so the trace. Okay? So let me write here. What is R? R is Rx x0, Rx x1, Rx x1. Oh, you did the intermediate exam. So if this one is stationary, I'm picking up all the terms there. So what is that? This is the sum of Rx x0, which is 2 divided by n times Rx x0. But you know, this is equal to 2 divided by n sigma square x. So it depends on the power of x. But that is easy to compute. It's straightforward to put inside. That's you know how this is done. Okay? So we found what is mu mean square error. Which is this one. So this is the mu to use for adaptive system. It is 2 trace of r. So don't use this, use that. If you use this one, you make a mistake. Never use that. If you use this and you come to me and say, oh, it's not converging, I tell you, of course it's not converging. That is the condition for converging in the mean, but not in the mean square. Which means this, the step from here to there is the price to pay between, you know, the method that is iterative, which means I know R, I know all the covariants, to the method where I don't know R, I don't know P. So here is a slower because mu is smaller, but it's convergent to the mean square. I go and get coffee, whatever, and meanwhile I search for other examples.